Hi there, this is Ming Yi from National Tsinghua University. Here I'm presenting enabling Android and API flow for TVM runtime. Uh, this is a paper that is submitted to ICPP-EMS 2020, and here we have four authors, including me, who are Ming Yi Lai, Jia Song, Zheng Kunli, and Ming Yu Hong. Two of those are from National Tsinghua University in Taiwan, and the other two are from MediaTek. For the content of this presentation, we have five big topics, which are introduction, background, the engineering architecture to convert Relay IR into an API, and the graph partitioning algorithm we used, experiments, and finally the conclusion. For the introduction background, we introduced TVM, Relay IR, and an API. TVM. TVM is a compiler stack for machine learning. It takes in artifacts produced by various machine learning training frameworks like TensorFlow, Keras, or MXNet, and converts them into a high-level differentiable IR, which is the internal representation of the machine learning graph in TVM. This graph is then optimized and lowered into implementation using another IR in TVM. The result of that lowering is again optimized and further lowered into binary code or ALVN IR to be converted into programs. On the right hand side, this is OTVN, and it's an optimization technique used in TVM, but it's irrelevant in today's paper. So Relay IR. Relay IR is the high-level differentiable IR in TVM, and it's the bridge between TVM and other machine learning frameworks. So TVM provides Python API that parses the artifacts from other training frameworks and converts them into TVM Relay IR, which is further lowered into tensor level IR and finally to binary or ALVN IR. NNAPI. NNAPI is a machine learning operator level API exposed in the C language in the Android operating system. It's intended to be used by other machine learning frameworks to define graphs, which can be executed on Android phones using an API's various hardware backends like DSP or vendor-specific hardware or GPU. So it's because an API is located on the operator level, so that we chose Relay IR and TVM to be the bridge in our study. So this is the engineering architecture that converts a TVM Relay IR module or graph to Android API. So on the right-hand side, we have the top-level architecture, which takes input in Relay IR, which is a graph, and this graph is then passed through a graph partitioner that partitions it into two parts. On the left-hand side, we have those that are left in TVM, compiled by TVM. And on the right-hand side, we have those that is outsourced to an API, which is passed through a external compiler that converts it into a TVM C source module. And this C code that can be compiled by the C++ compiler in Android NDK. The results of the left-hand side and right-hand side can be combined into a single TVM module, and this TVM module can be taken by the TVM C++ runtime on Android. And there's some further detail in the external compiler, and that is, in this external compiler, we use a parser to parse Relay IR into a JSON representation. The structure of this JSON representation is designed to closely mimic the structure of an API model, which means it can be easily lowered into a piece of C code that is the API model. And this C code can be wrapped by the TVM coding convention, which produces a TVM C source module. In the third big topic, we talk about the graph partition algorithm we use. So here we introduce the algorithm itself, and then we give a little example about it. The algorithm itself is consists of two DFS visits, and the first one is a post-order DFS visit, which visits the graph from the input to the output. And the second one is the pre-order visit, which visits in the opposite way. So in the first DFS, we use dynamic programming to compute the cost of these nodes. And here we show the transition steps of the dynamic programming algorithm. So the idea behind the transition step is quite simple, and that is we want to find the minimal cost to produce the result of the specific node on a specific device. So for the example on the right, we want to produce M1 on TVM, which is M1 is the result of OP0. So we want to get the result of OP0 on TVM. And to achieve this, there's two possibilities in our study. The first one is to compute OP0 on TVM, and the second one is to do that on an API. So to perform OP0 on TVM, we need to get its input, which is M0 on TVM. And associated with that, there is a cost of producing M0 on TVM, which is assumed to be minimal from previous DP iteration. So we take this cost and we add to it the cost to perform OP0 on TVM to get the result of it. For another possibility, we compute OP0 on an API. So again, we need to get the cost to produce M0 on an API, and we add to it the cost to perform OP0 on an API. But different from the first possibility, which is producing OP0 on TVM, since we're computing OP0 on an API, but we want the result on TVM, we need to insert the data movement cost to the second possibility. So that is why here we have a minimum operator here that chooses the one that the cost that is smaller. So after this, we can get the cost to produce M1 on TVM. And actually, we need to do the same thing for an API, and that is to compute the minimum cost to get M1 on an API, because we need both of these two costs to enable the next iteration of the dynamic programming algorithm. So here we are going to go through a small example, and in this example, it's really simple. We have only two operators, which is a convolution and another operator called dance. And here we have the cost matrix for these two operators to perform it on TVM or perform it on an API. And then finally, we have the data movement cost set to 5 for simplicity. So for the first step, we initialize two matrices. The first one is the main cost matrix, and the second one is the main cost device matrix. The main cost matrix holds the minimal cost to get the result of a specific node on a specific device, and the main cost device matrix holds the choice we made to get the minimal cost. So and that choice is on which device we perform which operator. So the initialization is like this. Uh, for I, which stands for input, W convolution 2D, which is the weight of convolution 2D, and W dense, which is the weight of the dense operator. We set the cost of them to produce them on TVM. We set it to 0 because these matrices should be on TVM at the beginning. And to get them on an API, we need to add 5 to that because we're moving the data. And for the main cost device, everything is set to TVM because each every of each of these nodes are on TVM at the beginning. And for the next step, we visit convolution 2D. So here we can see that the minimal cost to produce the result of convolution 2D on TVM is 25. This 25, it comes from the cost to move. It comes from the cost to perform convolution 2D on an API and move the results back to TVM. To perform convolution 2D on an API, we need the I matrix to be on an API, the W convolution 2D matrix to be on an API, and the computation cost itself, and finally the data movement cost. So that's like 5, 10, 20, and 25. So that's how we get 25 here. And for 20, the cost to produce the result of convolution 2D on an API, it's actually quite similar, except that we don't move the data from an API to TVM. So that's 20 and 25 here. So the main cost device, we set both of them to an API because in both cases, the computation is performed on an API. So for the next step, we visit the dense operator. And okay, so the minimal cost to produce the result of dense on TVM is 30, and that comes from the minimal cost to produce the first argument of dense operator, which is the result of the convolution operator on TVM. So we need the result of convolution 2D on TVM, and that minimal cost is 25. And then we have the cost of W dense, which is another argument to the dense operator, and that's 0 because it's already on the TVM managed memory. And finally, we have the cost to perform the dense operator on TVM, and that is 5. So adding these 3 items, we get 30 here. And for the dense operator's result on an API, it's coincidentally 30. Okay, so let me break it down. It's performing convolution 2D on an API, and then getting W dense on an API, that's a 5. And finally, performing the dense operator on an API, and that's another 5. So we have 2 5s and 120, and that gives us 30. The for the main cost device, the entry is now different. The dense operator was performed on TVM, so we put TVM here, and for the NAPI case, we performed it on an API, so it's an API here. Okay, so right now we have already computed the minimal cost to get the result of these nodes on TVM and an API device, but what's more important is actually the main cost device, which keeps the record of how we get the minimal cost. So right now we need to do the pre-order visit to partition the graph. So here we start from the output output, the parenthesis output node, we want these nodes to be on TVM because TVM is the main framework. So starting from output, which is the result of dance on TVM, we can see that dance itself it's assigned to TVM. So the dance node is blue. And then we visit convolution 2D. Okay, so to get the result of convolution 2D on TVM, we can see that the operator is performed on an API. So convolution 2D is the green node here, and for the argument to convolution 2D on an API, we can see that both of them are on TVM. So these two nodes, I and W convolution 2D, are blue. They are blue. And finally, we have the W dance node, which, according to the table, uh, is on TVM because here the dance operator is performed on TVM. So we look up W dance with TVM and it says TVM again. So on the right hand side is the partitioning result of the algorithm. Okay, so here we have the experiment results of our framework, and this is a speed up graph with respect to different models. Here we have the NNAPI 5, AlexNet, VGG16 and 19, and MobileNet V2. For the NNAPI 5, the result is actually quite good because for API level 28 and 29, which corresponds to different versions of the Android operating system, the speedups are quite good because in these cases, each every operators in the graph are supported by an API, so we can fully export the graph to an API which utilizes hardware accelerators. But for other cases like AlexNet, VGG16, and 19, it's not that good because some of the operators are not supported by the Android operating system, so we have to split the graph, and that results in some quite noticeable overhead actually. And the same thing can be said for MobileNet V2 because it's actually uh, it's actually a more fragmented graph because now for the yellow bar and the green bar in MobileNet V2, we can see that the result is actually quite poor, and in these two cases, the graph is actually split into a few dozen subgraphs, and that causes a lot of data movements. Yeah, so this is the speed up. Oh, sorry. Okay, so finally for the conclusion, this work it enables API for TVM, which is beneficial because we think that an API utilizes vendor-specific hardware accelerators, which is hard to achieve with pure TVM. And the experiment of the NNAPI 5 actually shows the potential of combining an API into TVM. So that is actually the main reason why we do this study. Okay, so that's all. Thank you.